Okay, so for homework 2, the first question for homework, not the first one, the second one, which is 1.33, the question is something like that. There is a fixed surface here and there is a moving plate here, okay? And in between these two plates, there is a fluid. The velocity profile for this applied force is this one, okay? Now, if you look at the profile, it's not linear. That means at each point, the velocity gradient is not same. So you need to calculate the velocity gradient at a specific point if you want to do something. And since it's not linear, they give you the equation for the velocity profile, which is u equals to, if I can remember correctly, it's 8y, this one, right? And one note, y is in millimeters, I guess, right? So you need to make sure you are using all the y value in millimeters because that's how this equation was developed. Now you need to find the top stress and the bottom stress here. And we also know the equation we need to use is tau equals to this one, right? Now you see here, we need du over dy, but we have the u, we don't have the du over dy. So there is one extra step and there is one question about that. What will be the expression for the velocity gradient? Okay, so you need to use your calculus practice here. That will be d over dy 8y minus this one, right? And if you differentiate 8y with respect to y, what will be that? Just the 8. And here it will be 0.2 multiplied by 2. It will be 0.61, right? Now, when you are calculating the shear stress at bottom, what will be the y here? Okay, there is one thing. In your question, they already told you from where you have to start the y scale. If they didn't tell you, you could decide which part, like from top or bottom you want to start. But they already said it's from bottom. So at bottom y equals to 0. And here y equals to what? 4 millimeter. So the value is already given in millimeter. You don't need to do anything. You can just directly use that 4 on this equation. Okay. So that's what you will do. At tau bottom, y should be 0. At tau top, y should be 4 millimeter. And that's how you will calculate the shear stress at top and bottom. Now, one thing on Canvas, most probably I interchanged the answer. For top, I entered the bottom answer, and from the bottom, I entered the top answer. So even if you get the correct answer, maybe you'll see it will tell you it's the wrong answer, but I will fix that today. Okay. So hopefully, if you do the homework this afternoon, hopefully you will not have the problem. Okay, that is one thing for 1.33, and for 1.5. Sorry, 1.35. The question was something like that, like there is a shaft here and it's the bearing and it's like you're pulling like this way. You just need to make sure which area is actually in contact with fluid, okay? So here, which area is in contact with fluid? Just surface area of this part, like this shaft. And since this is like circular in size, you know the diameter, so you know what will be the surface area, 2 pi r 8, something like that. So you can calculate the area, right? So that will be the I think most confusing part for you, maybe, like that's where you will do the mistakes, but make sure you do that. And for question number 1, Any one of you have any answer for question number 1? Did you calculate the density or specific gravity, specific weight for the lab experiment? Okay, do that and make sure you use the correct unit. Okay, in SI and SPS. For SI system, the density should be above 800 at least. If you get 1, 2, 0.5, 0.3, that will not work. It should be above 800 kg per meter cube. Okay. Okay. So I think once you start working on homework 2, you will have more questions. In that case, just email me. I will try to answer. Okay. Okay. So for today's lesson, we will start the second part of this course. Please make a bold note. Lecture 8 and 9, that is not included in your test 1. Lecture 8 and 9, that is not included in your test 1. So not included in your test 1 will be from lecture 1 to 7. 8 and 9 is just the second part. It will be for test 2. Okay. So we will and you will have the same class lecture for today and Monday. So Monday you will not have any new class lecture. Make sure you bring the class lecture on Monday also. Okay. 2 reminder, the homework 2 plus quiz 2, that is due before Monday class period. Everything will be available on Canvas within this afternoon. So if you want to work on those over the weekend, you can do that. Okay. Okay, let's start. For today's lesson, you know most of the part, you know pressure, you know the absolute pressure, gauge pressure. So it will be quick review for first part of this class. In second part of this class, if we have time, we will do something new. Okay. So remind me, what was the pressure? We discussed pressure and shear stress both. So pressure was what actually? That is exactly the same definition for shear stress. So there is one specific point you need to make sure force is parallel or perpendicular. Yes, you need to make sure, mention that part, that force is perpendicular to the cross-sectional area. And sometimes we name that as normal stress, right? And if it's parallel, we will call that shear stress. We are not discussing shear stress here. From this part, we will discuss the normal stress or pressure. So basically, the definition is force acting normal to an area divided by that area. So if that is the area and that is delta F, so at any point, the pressure will be the small part of force over that small part of area on which that force is acting. Okay. And if we have a surface area where the pressure is uniformly distributed, we will say that the average pressure is capital P equals to F over A. And we will mainly use that equation a lot. If P equals to F over A. Okay. So P is force here. P is the pressure here. Force is the area, and F is the force, and A is the area, cross-sectional area. And the main thing is F should be perpendicular to the area, right? Okay. So this is the Pascal's law. What he said, the intensity of the pressure acting on at any point. This is point A, this is point B. On point A, every direction, the pressure will be P. It doesn't matter from which side you're calculating, it should be always P. Now, for particle B or molecule B, what will be the pressure in each direction? This time it's what? P naught, right? So At any direction, it will be P naught. Now, one thing to mention or remember, P is not equals to P naught. The magnitude of force at each point can be different, but on each point from any direction, the pressure will be same as long as there is no shearing stress. Okay, so this can be a good example. If you pour some water inside the balloon, and if you make some hole, if you apply the pressure, the force at each point, the pressure at each point, it should be same. Okay, I wanted to make that for this class, but I couldn't do that. Maybe at some point I do that. So that is the Pascal's law, and we will use that assumption for any cases we will use here. Okay, so that is the Pascal law. Now,
So what's the difference in A and B?
if just the location of A and B. So maybe if you measure from the top, maybe A is in like 1 meter below the surface and B is the 2 meter below the surface. So it's just the location, and there can be hundreds of molecules. It's just two representative molecules here. Okay. Now, here again some review. Can anyone tell me what was the absolute pressure, what was the gauge pressure, and what is the relation between those two? Yes.
Absolute pressure was starting from 0.
0 means from the vacuum, right?
Yeah.
Okay.
And gauge pressure is starting from 1 atmosphere.
So gauge pressure is, it's not 1, it's just from the atmospheric pressure, which we consider 0, right? So that means from here, everything will be P absolute. From this point, if I use a different color here, from this P atmospheric, it can go this side, everything it will be P gauge pressure, right? And we also know there is a relation between what is the relation between P absolute and P gauge? What I need to add or subtract or do something? What will be the relation between these two? Gauge pressure is when we measure something from the atmospheric pressure. So if I want to get the absolute pressure, I need to do what? Add the atmospheric pressure. Yes. So that is the relation. We already know that. So this is a quick review. Again, unless I state something specifically, every pressure will be gauge pressure here. Okay, everything. And if there is something we need to do absolute, I will mention that, okay, it is absolute pressure. Or for your ideal gas law, you know the pressure should be absolute. So when you write down your equation, just make sure that is the absolute. Other than that, we are not using any absolute pressure at any point. Okay. If we use that, I will mention that. Okay. Now, again, remind me what are the units for pressure? It's force over area, so newtons per meter square or psi or feet square, right? Because inch square is not the standard unit, so we can use pound over feet square also, right? Now, just to give you some sort of idea what is 1 Newton, it is just the coincidence. It's not the actual reason of. If you take a normal size of apple and the force by which the apple is attracted to the earth core, that is actually kind of 1 Newton. So it's not related to that history that there was apple fell from the tree and he discovered the gravity, but it's kind of same that the weight of the apple is 1 Newton, and you can imagine 1 Newton is not that big, right? So that's why most of the time we use kilonewton per meter square or megapascal, kilopascal, something like that. Okay. Okay. Are we good? It was a good review. Okay. Good. So I'll go through very quickly. Now, the actual second part of this course will start. Till now, we discussed all the fluid properties, like the inherent properties, what will be the fluid properties. Now, we will use those and we will try to explain when the fluid is in motion or when they're in rest, how they will behave. Okay, yes.
So is this what starts the information for test 2?
Yes, yes. So, and for this pressure, since we need the pressure, absolute pressure, gauge pressure, I thought that will be a good review if we go through those again. So, static means what? When things are not moving, or maybe they are moving with a constant velocity, no acceleration, like there is no up down of the movement. It will be the same constant velocity. So, I tried to add few examples here. Obviously, there are hundreds of more examples. The most right one, this one is what? The Hoover Dam, right? And do you think the water here, they're stagnant or they're moving?
It's moving.
If it's stagnant, there will be no hydropower. It's moving, but with a very constant, relatively constant velocity. So that's why we can consider that as a static. At the same time, this is a tank where, like you will see this type of tanks in any industry where they store water, oil, different type of liquids, sulfuric acid, something like that. This is another example like a canal inside the city. Obviously, this water is moving in some direction, but with not that much velocity, and there is no like huge velocity change or something. But as an engineer, you need to design this, right? Just think about this wall. A huge amount of water pressure is on this wall, right? Now, if you don't design this wall to withstand that pressure, what will happen? It will it will be broken and it will be a disaster. Thousands of people will be killed, right? So that's why we need to know how we can calculate the pressure of water on something or force of water on something, or when they are not moving or they are moving with a constant velocity, how can we find out their characteristics? And that's what we will do this part, the hydrostatic pressure and everything, okay? So that's what we will do for next few classes. And how can we measure the pressure? How can we measure the force? If it's straight wall, if it's curved wall, how can we do that? That's what we will do in this part, okay? Okay, so the static pressure variation, few minutes ago, we discussed the Pascal law only for one molecule, right? Now, and we told, like, we discussed that from any direction, the pressure is same. Now here, if we have a tube of fluid here, like here, we want to identify, we want to define what will be the pressure variation in horizontal direction or vertical direction. If you remember here, I said that P is not equals to P naught, right? That's what I said. So we need to identify if it's not same, what is the variation, or why I'm saying it's not same. I need to identify that. So what we will do, we will try to calculate the pressure variation in horizontal direction and in vertical direction. Okay. So at first we will do in horizontal direction. Okay. So since now we will use some concept from your statics class. Do you remember in any direction the summation of force will be zero when it's in equilibrium. We will exactly use that concept. So that is the axis. Since they are using y, I will use y here. And I will use the definition of pressure, Fa. So the force will be what? P times A, right? Now, if you look at this number, are you seeing a small p and a delta A? That's because since this is a very small cube, a small pressure, the differential pressure is applying on this cross-sectional delta A. That's why the force here, delta F, is P delta A. Okay? So I will use the Fy direction, and in Fy direction, this side is positive. Maybe you use some other notation for your statics, but the top sign here, it simply means if I go this side, in the left side, the sign convention is positive for this case. Okay. Did you use the same thing for your statics, or how did you define like which direction? Okay. It is same everywhere, I guess. Okay. So tell me how many components I have in y direction. In force component. Two. One is that P delta A, right? And there is another P. This is the P. This is A. So this is, if I define these one, let me write down one more line here. Oops. I will write down one extra line here. So I will define this one as delta F1, and I will define this one as delta F2. Okay. So the direction for delta F1 is positive. What is the direction for F2?
Negative.
Yes. And the summation of this one is 0. So now I will write down P delta A, and here I have P equals to 0. Okay. Now I will remove the parentheses and I will multiply this delta A with each term inside the parentheses. Okay. So that will be the case. Stop me if you don't get it or if I'm doing something wrong. Okay, so P delta A and P delta A, can I cancel those two terms? Because that they are same, right? Okay. So what will be the next line? Did I remove everything here? Oh my God. Erase all of. Okay, I will do that very quickly. Ah, okay, you have that, so I will do that very quickly. Okay, I'm not writing all the details here. So, and the pen is not working. Okay, so P delta A, P delta A, and minus, what was that? y equals to 0, right? And then we cancel these two. So we will have this one, this, right? Now, I'm sure you know if we have one equation like that, like x multiplied with y equals to 0, either x is 0 or y is 0, right? That is the logical thing to know, that either x is 0 or y is 0. That's why the result is 0. Now here, area can't be 0. Delta x can't be 0. Delta y, it can't be 0 also, because we obviously we are considering something which has some dimension, right? So these two can't be 0. So the only option is if delta y and delta a can't be 0, which parameter will be 0 here? The pressure is 0 and the variation of pressure is finally 0. I honestly don't know why I'm getting that line. Sorry about that. Okay, so if the delta P is 0, what does that mean? Delta P is what? Variation of P, right? So if I say delta P is 0, it seems or it means horizontal direction, pressure variation is what? Pressure variation is what? And if the pressure variation is 0, that means pressure is constant, right? And that is the thing you will remember. In horizontal direction, there is no variation in pressure. As long as they are on the same level in horizontal direction, there will be no change in pressure. Okay, so if this point, the pressure is like 50 kilopascal, what will be the pressure at that point? 50 kilopascal. Okay, so that is one statement. In horizontal direction, there is no pressure variation. Okay. Now I want you to do the same for vertical direction. So if you go to the next part of the question or your class lecture, there is the same thing, only change is this time it's the vertical direction. Okay. So I want you to work on that part before starting that. Tell me how many different components you have in like in vertical direction. This time it's 3 because this one is F1, this one is F2, and this one is just the weight. And you can consider these as a positive. So if Z is as a positive equals to 0. Now write down all the things and try to come up with the statement about vertical direction. What is the pressure variation at vertical direction? Okay. So I'll be here if anyone have any confusion or any help, just let me know. So I'm writing the very first line. What will be the direction for F1? Positive or negative? What about F2? What about W? Okay, so you know that. Now work on that. I will work on that after 2 minutes. Just try working on that. Got wrong answer. No problem. So for F1, F2, W, write down everything you have here and then try to cancel some common from every part. And F1. The W, if the gamma is the specific weight, and delta A, delta B is the one. Write down that. So here, I just said that gamma delta A delta Z is W. How did I get that? So you have to start with the specific weight, which is weight over volume, right? Since we are looking for force, W equals to gamma times volume. And for this cube or this, like this fluid particle, the what will be the volume? Delta A times, tell me what will be the volume? Yes, good. So it will be gamma delta A times delta Z. And that's what they're saying here. Okay? So that is the W. If anyone has any answer, whether it's 0 or something, let me know. I know all the company of the same time. Same time. You get it? Here, you have something like that. Okay. Anyone have any sort of answer? 0 or some anything? Here, you can actually write down delta C delta. You have the length here, the delta. Basically, this delta T or this P or this basically is the difference of right? Some sort of distance. You can write down this delta C. You can, but you can't consider this. What you can do instead of this, you can write down you can something. You don't have it. Now you can use something because you're trying to calm down. Got something? While you are working on that, I will write down here. So F1 is what? P delta A. F2, if I skip one line, it will be delta dP over dz, delta Z, delta A, right? And the W will be what? Gamma delta A and delta Z. Goes to 0, right? Now I can cancel these two. Finally, I have what? If I move this one on the other side, gamma, delta A, delta Z. Now I have delta A, delta Z on both sides. Can I cancel those two? Okay, let's do that. So finally, I have what? Gamma, right? And if I just move the sign, here. So what does that mean? Is the variation of pressure in vertical direction is 0 also, or it has some value? Okay. And it will depend on what? Obviously delta Z in the specific weight, right? Now just think about that. If you have 1 glass of water and 1 glass of molasses, I hope molasses specific gravity, specific weight is greater than the water. Yes. So which one will create more force on the surface? Here. If I have 1 glass of water, 1 glass of molasses here. Molasses, that's because molasses individual weight or mass is higher than the water particles, right? And here you can see the same thing, that if the pressure on the Z direction, it will depend on the specific weight. At the same time, it will depend on the height also, because if you have 1 glass of like 10 feet of water and 5 feet of water, obviously the 10 feet will create more pressure on the surface, right? Because it's the more material. In easy word, the more material the fluid has, it will create more pressure. So basically, the equation is saying that the Z will give you the height and the gamma will give you the fluid properties. Okay. So for same type of fluid with different height, the pressure can be different. With different types of fluid with same height, pressure can be different. So there are two factors, Z and what? The gamma, right? Okay. So I will keep that equation here. And what will be the statement? If I want to write down here, in vertical direction, pressure variation depends on what? Density or specific gravity, specific weight or fluid properties, right? Specific weight of the fluid. Okay. So remind me again, what was the pressure variation in horizontal direction? Okay. And what is the pressure variation in vertical direction? First thing, it's not 0. Second thing, it will depend on the specific weight of the fluid, or you can say the density of the fluid. The specific gravity weight is actually density times G. Now, this equation is true for any type of fluid, incompressible, compressible one, but we need to come up with more like definite expression. That's what we will do now. Are you done, everyone, with this slide? Okay. So what we will do now, we will come up with the explicit expression for incompressible and the compressible one. So I will just start the incompressible one today, and we will work with the compressible one in next class. Give me one example of incompressible and give me the definition of incompressible fluid. Okay, that is the example. water or any liquid, right? And what should be the characteristics of incompressible fluid? Volume can change, or you can't compress the volume, right? Okay. So if volume is not changing, that means the specific weight or density is not changing, right? So, okay. So this is the main characteristics, and we know the example will be water or any liquid. Now, from your previous uh, slide or something, what was the pressure variation?
Is that pressure or density?
Here is the density. I was saying to my section 1 that I should go to a writing class. In our 11th grade, like I went to a missionary school, so there were lots of sister and brother. They came from here, Bangladesh. They ran lots of school there. So we had one class where one sister taught us how to write ABC in different form, like fonts. Like it's, that time we didn't know about that, like Times New Roman or something like that. But we had to practice ABC. Like that was just the class, 1 day per week. Okay, so that is the equation, right? The pressure variation in vertical direction. Now, when we develop that equation, can you tell me in which direction we consider z as positive? Upper direction? That is the usual norm, right? But here, what we will do at the surface of any liquid, since it's open to atmosphere, the pressure is at the gauge pressure is what? Yes. So gauge pressure is 0 at the surface. So just for our convenience, this time we will consider the scale from top. Okay. And that should be the Z scale positive. Okay. And if we have this, if I want to integrate that, what I need to write down? Delta P, delta Z, gamma, right? I need to write down this one. Now for incompressible fluid, gamma is constant. Can I take that out of the integration sign, the summation sign? Can I do that? Here. I will do that. And I should use something here. Now I need to use some limit. If I start my Z from the surface, it should be Z naught to Z, right? What should be the limit for P at Z naught? Pressure is what? And at this point, what is the pressure? Just P, that's what they gave you, right? And I will modify a little bit. This one, they already gave you the, okay. So at this point, Z is 0, right? And at this point, what is the Z they gave you? H, yes, the height. Okay, so that should be the limit. So if you remove the, or if you integrate that, it will be P 0 or what? This one, right? Did I write that properly? Thank you. Actually, that should be P naught. Here. Just P naught. Let's not decide right now that it was 0. Okay. That should be P naught. So P minus P naught equals to what? Gamma H, right? I made a little bit mistake here. Let's check what I did. So from this point, that is 0, the pressure is P naught, Z is 0. At this point, Z is H, the pressure is P. So P minus P naught, gamma H minus 0, P minus P naught. I think I made a sign mistake because it should be P naught plus gamma H. What did I miss here? So at this point, it's P, we are using the opposite scale. So at P, at Z equals to 0, it's P. And at H, it's actually the P. I think I did that correct. But for some reason, I'm getting the opposite answer. Okay, you will get 1 extra point if you find out what I did wrong. Quick, you have 2 minutes. What did I just do wrong here? So you're saying it should be from 0 to 8, it should be H to 0. That's what you're saying? Okay. Yeah. Good. So you, okay, who found out the answer? You both will get 1 extra point. Just remind me, okay? Okay, remind me where for your homework 2 or something. Okay, so it should be H to 0. So that means, thank you guys. It should be 0 minus 8. That means, okay, that is the equation here. And who can tell me P naught is actually what? Again, 1 extra point. P naught is 0 in what scale? Gauge. So in general comment, it should be atmospheric pressure, right? So it will be 0 at gauge scale. And if I use the absolute scale, it will be either 101.3 kilopascal or 14.7 psi, right? Okay, those of you gave me the correct answer today. Write down that note on your homework too. I will give you 1 extra point. Okay, I will stop here and please, everyone, please complete this one and we will start from this point on Monday. Okay? Oh, I forgot to tell you one thing. I will upload some practice problem for the test 1. So please go through those. I will upload the solution later at some point. This time you will just try by yourself. If you want to get some extra point, you can submit the solution to me, but that's not mandatory. It's on you. And Monday, ask me question if you have any question about those class problem or practice problem or anything. Okay? Okay. You have a good weekend. I'll see you on Monday.